Recording's rolling. It is Wednesday, September 24. You guys are gonna finish these labs today, but actually, before you do, I do want to debrief you guys to show you what ideal solutions would look like. So you can gather data for a couple of days, maybe try to make these graphs and equations. We want to make sure that you know that you're on the right track and you know what you're doing. But don't worry about this right if that's AD, but besides that. Okay. And then tomorrow we'll do textbook puzzles all day. So that's fine. All right, so let's start with the friction side. Remember, there were two halves to this friction side, like two setups, and they were both trying to address the same question, which is what is the coefficient of friction between two surfaces? Now, remember, this is a material property. So if you have, say, like this metal versus regular paper versus sandpaper or versus wax paper or that aluminum track right there, you'll get different results because those are all different materials. Okay, and remember what this coefficient of friction is. This is Greek letter mu. It's the ratio of this friction force compared to this normal force. You can think of it that way, right? You divide on normal force. Right? And actually, what you're looking at right here, this picture, is the first setup. Right? So all you did was you pull different weights. You guys had whole box of lab weight, box of lab weights. You pull with this the spring scale right here, which is shown right here. And because as long as you're pulling at constant velocity, then this would work. Because what was important again about constant velocity? Equilibrium. Yeah, equilibrium. So all the forces zero out, which means that the force being on the spring scale is exactly equal to the friction force. And the weight would, well, in this case, pulling horizontally on a horizontal surface would be exactly equal to the normal force. Okay? So here, I'm just going to make up some numbers. Let's say you had weights of like 1 Newton, 2 Newtons, 5 Newtons, 10 Newtons. So and maybe the pull is like, maybe like a quarter of a Newton, maybe it's like half a Newton, maybe it's like about 2 or 3 Newtons. Yeah, whoops, that's not what I meant to do. Maybe it's like 1 or 2 Newtons, maybe it's like 3 Newtons, I don't know, something like that. Whatever. Okay. So can you take the ratio of those? So this would be like 0.25, this is like 0.25, 2 over 5 is like 0.4, 3 over 10 is like 0.3. And you should be getting approximately a consistent ratio. Now, those aren't real numbers, I just made them up right now. But see how they're all kind of hovering about 0.3-ish, about somewhere there, about 0.3? Okay. So then if you made a graph, now I wrote F pull versus F weight, but really that's kind of a stand-in for, see, this is F pull and this is F weight. Isn't that really just a stand-in for friction force compared to normal force? Okay. So what is your friction force as a function of your normal force? Or you could put, I have the title right here. So guys, did you all start your axes at 0, 0? Right, start at 0, 0, and you scaled accordingly. So you're like 2 Newtons, 4, 6, 8, 10 Newtons. That can either represent the weight or the normal force. Same idea. And then going up, maybe like 0, 1, 2, 3 Newtons might be up here, something like that. Notice how they're all scaled linearly. They start from 0. And then you plot these points. So maybe you get points like, you do kind of a fast version. But ideally, these all line up in a straight line. Right? Maybe somewhere a little above, somewhere a little below. That's okay, right? But you should get some version of a linear relationship, which means you can make a linear relationship equation if you can find out the slope of this line. And the slope of this line is really kind of like the average of all these, which is about 0.3 in my case. Yeah, I'm just kind of making stuff up. So the equation would go the pulling force, or the which would represent the friction force, also would be in my case I'd get about 0.3 times the normal force or 0.3 times the weight, something like that. That's it. And then you could use that to have predictive power. I mean, that's what physics allows you to do, right? Is if I ask a question like, what if you had a 30 Newton weight and you drag that across the same surface? You say, oh, well, 30 Newtons times 0.3, I bet it would take about 9 Newtons of force to drag it at constant velocity. Right? That's what that would mean. And mu in this case is the coefficient of friction. Coefficient, maybe I should say coefficient of kinetic friction, right? Because you're sliding, right? Right. So there it is, right? Or you could say the slope of the graph, same thing. Right? You guys see what that is? Right. Right. And then the second half of the friction lab, there's a completely different setup that also addresses the same question. What's the coefficient of friction? Now, this one's a bit more involved. So I see 3 forces on this block on an incline. What you do is you set these different weights on an incline. Right? You would raise the angle of the incline until it would naturally slide down at constant velocity, which again means equilibrium. So I see these 3 forces. Now the weight, I'll break into these components. We got a sine and a cosine component. I can go through this proof. If you're really interested in this proof, I might recommend either studying your thumbnails I give to you. I have this poster on my wall, or you could watch this video, pause this video, and maybe write this on paper. But at the end of this proof, the coefficient of kinetic friction ends up being the tangent of this angle. Again, as long as it's sliding at constant velocity. Right? So I had you guys try this experimentally. So maybe you had like the same weights, 1, 2, 5, 10, 8, wait, whatever. Right? He said, what angle does it slide down at constant velocity? Now, I've been looking at your guys' lab papers. So you guys can get somewhere between like 10 and 15 degrees. So here, I'll just make up what if it got something like that, for example. But it shouldn't really change. In fact, ideally, it turns out to be exactly the same. So what is tangent of all these? Here, I'll just pick one of these. Let's say 12 degrees, for example. Right? We got like 0.21 or what is tangent of 14? Let's see what that is. Like 0.25, right? 0.20 something. Right? Could you like find an average? And then if you make this graph, tan theta versus weight. So I'll put tan theta on the y-axis. So it's kind of like y equals something. Right? And then I'll put weight over here. Right? Again, start this at 0. So 0, 0. My weights went, let's see, 2, 4, 6, 8, 10. Okay. But tan theta should be approximately the same number all the way down. Okay, I can do the other ones real fast. What's tan at 15 degrees? This is 0.27. What's tan at 10 degrees is 0.18. These aren't real numbers. Again, I just make this up right now in front of you guys. Okay? But they do represent approximately what I've been seeing you guys get. You see how all these numbers are in the ballpark of about 0.2, something between 0.2 and 0.3, about 0.25. So if I had like 0.25 up here, like some of these are a little bit less than, some of these are a little bit bigger than, but it's pretty much a flat curve, isn't it? Is it just like a flat line? Okay? Guys, how do you make the equation of a flat line? Is it just y equals that number? Okay? That's all. But instead of y equals, it's tan theta equals. So I'll say, suppose the averages, it got about 0.25, but let's think about what it is, right? Like that. And how does tan theta relate to the other side of the slab? Well, you might be able to see it here. You guys see how that number and that number are extremely close to each other? They're about the same thing, right? In fact, looking at your guys' actual data, I got plenty of groups so far today that got them even closer than I did, like 0.25, 0.3. Like that's almost the same number. I saw some groups that got like 0.29 and 0.29, so it was like the same. Okay, well, that's really good. So the coefficient of kinetic friction is tan theta. Okay? They're the same thing. They're the same thing. Okay? There's two different ways to get there. Okay, you guys get that? So recap so far. Friction lab. Here's one way to get friction. It's kind of the definitional, straightforward way of getting friction. Okay? You drag, lift, take the ratio. Okay? And here's a alternate way that has a little proof attached to it. And it turns out the tan and the theta also represents coefficient of friction. Right, now, to the other side of this page, we got some Atwoods going on. So you guys were hanging different, here, let's start with the classic Atwood. You hang different weights and say that how far does it move and how much time starting from rest. And you could kinematically calculate the acceleration. That was the last column here. Right? You compare that to the gravity field. And then at the bottom says, can you come up with an expression for acceleration in the setup as a function of the input masses and whatever gravity field you're in? Now, the answer is on this page here, which again is in your thumbnail notes. I gave you the first day of school, and it's also on my wall over there. So I'll walk you guys through the logic of how you can determine this with dynamics. Right? And then you can compare that to what you got kinematically by calculating acceleration. So I have these two weights, and there's these two downward forces. Right? So when this weight and this weight, isn't it like kind of like a tug of war? Right? Tug of war. Right? In fact, if they were the same, like, what if I have these two do exactly the same? Did you guys try that? And what did it do? You let them go, and they just did what? Nothing. They just sit there. So that would correspond to zero acceleration. That might give you a hint as to one part of how it's correct. Now, there's a tension force also connecting them, but you don't actually need the tension to calculate the acceleration. The reason being, this is just internal to the system. So, kind of like I move this pen around, and there's a bunch of plastic molecules that are all pulling on each other, but it doesn't really have anything to do the net motion of the center mass of the pen. That has to do, no, I'm providing an external force, and that's affecting the motion of the pen. That's like these external forces here. So I'm going to go to Newton's second law of motion. You guys see this pink box says Newton's second law of motion. Acceleration is the net force acting on mass, the total mass. Now, the net force, if this is like a tug of war, okay, but these add or subtract from each other in a tug of war sense. They subtract, right? This one says let's go clockwise. This says no, let's go counterclockwise. See how I subtracted out the weights, subtract weights, okay? And how much total inertia is that difference in force moving? Oh, well, that's the sum of the masses. So it's difference in weight over sum of mass. That is the answer right there. You see that gold box? That's the answer to your lab. Or at least this box down here. Now I could factor out that G, factor out Earth gravity, and that leaves me with this. The difference in masses divided by the sum of the masses, and then all times the gravity field. In this case, this would be Earth gravity, which I gave you Earth gravity as a number right here. Now you can try this. So you guys might have some of this data, or maybe all this data if you got these in the last couple of days. You have your input masses, because you recorded those. You did the kinematic work to calculate what is the corresponding acceleration. produced so far and so much time started from rest, you can calculate the acceleration, and there's the expression how to do that. Right? I bet if you plug in this here, so difference masses over sum of masses times 980 centimeters per second squared, I bet it'll land you fairly close to this box. Right? You guys can try that out. Right? Now there might be a little friction in this wheel, or maybe even this has a tiny bit of rotational inertia. So maybe for the smaller lab weights, like if you try these two, it might not be super accurate, but for the larger ones, it'll probably be more accurate. Okay? And are you guys good so far? Little side thought here. I didn't talk about these green boxes yet. Notice these green boxes also have the tension force in them. So while you guys are digesting this, think about this. We might address this later. Is if you have the question, well, what is the tension in the string? Okay. You could either set up an equation just for block one, which is this equation here, or just for block two, which is just this equation here. See how like there's two opposing forces, so they subtract from each other and result times mass times acceleration just for block two. That's what this is, right? Or alternatively, some physics books and some physics instructors actually start with these two green equations. They set up a system of equations with these two. Say, just focus on block one, you get this equation. Just focus on block two, you get this equation. And then you can do a system of equations and also eventually reach this gold box that way. It also works out. Okay? And then the tension force cancels out in the end. Okay? Okay, but last debrief is this modified Atwood. So you guys also have this setup. Now, you guys have those low friction carts, like this one here. Low friction cart, get a little push, it just keeps going. Okay? So, like low friction. Okay, so we got rid of the friction. So what's the acceleration with the masses arranged this way? Right? Well, let's look at all the forces. Do you guys see how the hanging weight, it does have a weight force? Right? And actually, guys, this M1G, this is the only force that ends up mattering. All the other ones cancel out. Right? Because I did put the friction force here in light gray, but that's negligible, so you can just say that's pretty much zero. Right? Now, what about this mass up here? This mass 2. It has a weight, but it also has a normal force that's canceling it out. These two blue ones cancel. Okay, that. What about the tension? Oh, well, that's just an internal force, just like it was for the classic Atwood. So that one doesn't matter either in terms of the whole system. Right? The only force that's external to the system driving the whole system to move is the weight of the hanging one. Okay? So if you jump over to Newton's second law of motion, which is this heat box, and plug in the values, well, in place of the net force, you put in the weight of the hanging block, which I did right here. Okay? And then in terms of the total mass, like what's the total inertia being moved around? Well, that's the sum of the masses. You see that? And that right there, that gold box is the answer to this around here. Right? So it ends up being the first mass, or the hanging mass, right? Divided by the sum of the masses, right? All times the gravity field, right? Which is exactly what this shows right here. It says. Okay? And furthermore, if you want to know, I wonder what is the tension in the connecting string? There is a way to find that, and that's either one of these green boxes. Right? Okay, so there you go. There's the full debrief. Hopefully you guys are on the right track for those. You guys have today to get all your data and the equations and the graphs. So that's worked out pretty perfectly for my earlier physics classes. So go ahead. Everything you need back in the lab area, I will walk around and help you guys out.